Welcome back to Calculus 2. In this lecture, we're going to introduce an extremely useful topic to mathematics, science, and engineering with something called a Taylor and Maclaurin series. All right, if we think back to what we were talking about in the previous lecture, we were trying to find power series representations for functions. All right, and we could do this either for a power series representation in powers of x minus a, if we're looking for a version centered at x equal a, some non-zero value, or we can find a power series representation in powers of x centered at 0. Now, all the examples that we looked at kind of built off of using our geometric series power series, which we kind of re-expressed as 1 over 1 minus x equals the summation from n equals 0 to infinity of the term x to the n. And this power series representation is only valid for values of x in absolute value less than 1, or equivalently values of x between -1 and 1. Now, we did a lot of examples with that, either algebraic manipulation of this result, or by basically using the tools of calculus, like we saw in the last lecture, differentiating this, or maybe finding an antiderivative or integral of that. All right, now that works. We were able to find power series representations for functions that way, but it only basically is applicable if the function is related to 1 over 1 minus x. We're now left with the question, what do we do if the function is not related to 1 over 1 minus x? For instance, how would we find power series representations for these three functions down there, e to the x, sine of x, or cosine of x? That geometric series isn't going to help us, so we might need some more tools, and that's exactly where Taylor and Maclaurin series come in. They give us an alternate way to calculate the power series representation, as we'll see. Now, there's a second point of view that we can take to introduce Taylor and Maclaurin series. This goes back to your Calc 1 course when you talked about finding the equation of a tangent line, or a little bit later, what you called the linearization of a function at a certain x value. So let's look at this visually. So the setup is we have a function, could be a curvy function, and there's a point on the graph, and at that point, with x coordinate a, we're going to look for the tangent line, or calculate the linearization of this function at that x value. Now, you probably at least recall one of the main ideas early on in your Calc 1 course. The slope of a tangent line comes from the derivative. If you put that all together, apply basically on the left there, point slope form, you get this equation for the tangent line. The y coordinate would be f of a. The slope is now f prime of a. Now later, you manipulated that and took a different perspective on that, and you called this the linearization of the function at a. And you basically go from the equation of a tangent line, solve that for y, add f of a to the right side, and you get this expression for what's now called L of x, the linearization of a function at that x coordinate a. Okay, now what this basically does for you, we're going to be thinking primarily here, looking at the linearization point of view. What this basically allows you to do is, so long as your x coordinate is close to a, so in other words, on the graph, you're very close to that point, then the red tangent line, which we're now calling a linearization, is close to the graph. We rewrite that as saying the linearization value is approximately equal to the function value when the x coordinate, or x value, is approximately equal to a. Now, what a linearization does is it approximates the function with a degree 1 polynomial, or a linear polynomial, or linear function. Well, we might be asking, can we generalize or extend this to higher degree approximations? So instead of a degree 1 polynomial approximation, can we approximate the function with a degree 2 polynomial, a quadratic function? As it turns out, we can, and that's the alternate perspective for what Taylor and Maclaurin series will do for us. We're going to kind of see that in the second part of this lecture. Since this kind of gets very dense, we'll split it into two parts. Okay, let's go ahead and get into the basics of what Taylor and Maclaurin series are. And what we're going to look at right now is not a proof of, I'll say, the mathematical ideas, but just at least a kind of a way to see where these mathematical results come from. We're not going to worry about any issues of convergence. We'll just try to kind of see where this goes. And what we're going to be doing is trying to find a way to calculate the values of the coefficient C sub n in a power series representation. So can we, with the function, solve for the values of C sub n? So we have it written in summation form. Just write out a few terms. We're going to use this kind of and manipulate it. So we have f of x equals, and then write out a few terms, c sub 0 plus c sub 1 times x minus a, and then so on and so on. And let's think, if we try to find the values for the nth coefficients, let's start with the starting index 0 and see if we can solve first for c sub 0. Now, we're going to manipulate this like we would in an equation. We're going to use the tools of calculus, since we set that up for power series from the last lecture, finding power series representations for derivatives and antiderivatives of a function. And we can solve for c sub 0 by plugging in a. Notice on the right-hand side, you have x minus a to various powers. Think of what would happen if you replace x with a minus a is 0. So almost all of the infinite terms on the right-hand side evaluate to 0 when we plug in a. But what you're left with on the right-hand side, the only non-zero term, would be c sub 0. So if we plug a into this, plug it in on the left side, so you'll get f of a. The right side evaluates to just c sub 0. Well, and that basically is solved for c sub 0. We find the value of that, the first coefficient, which we label c sub 0, equals f of a. Now, how we're going to find the value for the next coefficient, c sub 1, is we're going to apply a kind of an idea from calculus, calculating derivatives for powers here of x minus a. So let's take our expression there for f of x and differentiate it. Now we're going to differentiate those powers of x minus a. For instance, x minus a squared, x minus a cubed, so on and so on. We're going to apply the chain rule. So bring the exponent down, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside. But if you take a look at the inner expressions, the part in parentheses, x minus a, the derivative of x minus a is just 1. So the chain rule, we just multiply by 1 at the end there, which doesn't change anything. So if we take our power series for f of x and we differentiate it, we get a power series representation for the derivative. Notice c sub 0, which is a constant, that differentiates to 0. C sub 1, which has x minus a multiplying it in the function's power series, when you differentiate c sub 1 times x minus a, that just differentiates to c sub 1, and then the rest of the terms follow by applying the chain rule. We can do the same thing as above. We can plug in x equals a now, and almost all the terms on the right-hand side evaluate to 0. That's because x minus a equals 0 when x equals a. But notice what you're left with on the right-hand side is c sub 1. And if we solve that, we get now the value for c sub 1 as f prime of a. So at this point, great, we have 2 coefficients out of an infinite amount of them. Now, we're not going to do this an infinite amount of times, but we'll go through it kind of a few more steps just to see a pattern that's going to emerge. Let's go ahead and take f prime and its power series representation and differentiate it again. So if you apply the chain rule and differentiate that term by term, again, we're going to save the issues of convergence and interval of convergence for later. We're just, again, seeing where this goes. We get this power series representation for the second derivative. We can solve for the value of c sub 2, kind of continuing. We have c sub 0. We determine c sub 1. We can now solve for c sub 2. And what we get is c sub 2 equals the second derivative at a divided by 2. And you can probably see what we're doing. We differentiate and then plug in x equals a to get the value of each next successive coefficient. Let's go through this one more time. We'll take the power series representation for f double prime, differentiate that one more time. If you do that, you'll have a way to solve for c sub 3. Notice I'm keeping the factors of 3 and 2 and 4 and 3. I'm not multiplying them together. There's a reason for that. We're going to kind of see a pattern momentarily. And we get a simple equation to solve for c sub 3. What you get after you plug in x equals a, you get the value for c sub 3 as the third order derivative at a divided by 6, or 3 times 2 as we have it expressed there. Now at this point, you can probably see what we're doing. We get the value of the next coefficient by differentiating and then plugging in or evaluating at x equals a. Now before we give the general result, which is leading to what Taylor and Maclaurin series tell us, let's rewrite the values for c sub 1, c sub 2, and c sub 3 so we can maybe see a pattern emerging. I can rewrite c sub 1. There's no denominator, but 1 factorial, which is 1. I can re-express c sub 1 as the first derivative at a divided by 1 factorial. I can write the denominator of c sub 2, which is 2. I can write that as 2 factorial, since 2 factorial is 2 times 1. And in the denominator of c sub 3, 3 times 2, I can express that as 3 factorial. 3 times 2 times 1. Now you probably can see maybe a pattern. Each coefficient, for instance, c sub 1, c sub 2, and c sub 3, in the numerator, there is an nth order derivative that matches the index. C sub 1 contains f prime. C sub 2 contains f double prime. C sub 3 contains f triple prime in the numerator. In the denominators of those coefficients is a matching factorial, a factorial that matches the index. 1 factorial in the denominator of c sub 1, 2 factorial in the denominator of c sub 2, and 3 factorial in the denominator of c sub 3. If we take a look at those versions written in red, now you might have a way to generalize that to a particular formula for c sub n. Now you can kind of keep going with this process of differentiating the power series representation and then plugging in x equals a. But at this point, with those 3 versions for the coefficients of c sub 1, c sub 2, and c sub 3, you can maybe hypothesize a formula. Give yourself a few seconds and see if you can write that down. All right, if we take again a look at those versions on the right in red, we might expect the coefficient value for c sub n in the numerator. There's a matching order derivative. So for instance, the nth order derivative now, it's evaluated at a, and then we divide by a factorial that matches the index. Since the index here is just general, n, we divide by n factorial. And as it turns out, this is correct. The value for c sub n if we were to continue with this process, we get it as the nth derivative evaluated at a, and this is a notation for when the order of derivative starts to get above probably the third or fourth order derivative. It's very awkward and tedious to write, for instance, 5, 6, or more primes to express an order of a derivative. So we switch it to putting the order in parentheses, but don't interpret that as an exponent. That denotes the nth order derivative, not an nth power of a function. All right, so that has the nth order derivative evaluated at a, and then we divide by a matching n factorial. All right, and that is the result that I wanted to work through a process of differentiation and then plugging in, we get values of successive coefficients. And that is the main result for what Taylor and Maclaurin series are. They give us a way to calculate the coefficients by calculating derivatives. All right, let's go ahead and summarize. Again, what we went through right here was just to see where this comes from, but let's go ahead and now summarize what Taylor and Maclaurin series are. Okay, a Taylor series, this is a power series representation for a function that is centered at some non-zero value a. Think back to when we started defining and introducing power series. We mentioned there were two versions we're going to see. A version centered at a, some non-zero value, or a version centered at 0. Here we have the version centered at a. What a Taylor series tells us is we can calculate the nth coefficient by calculating an nth order derivative evaluated at a divided by n factorial. Now this is a power series representation, but instead of arbitrary values for the nth coefficients, we have a way to calculate them, which is the main result for a Taylor series. All right, the other version for what a Maclaurin series is, it's just the version or special case when the center point or approximation point is 0. So instead of having the nth derivative evaluated at a, we have the nth derivative evaluated at 0. And pretty similar result. The only difference, instead of having powers of x minus a in a Taylor series, we have just powers of x in a Maclaurin series. All right, and again, notice a Maclaurin series is a special case of a Taylor series where the center point is 0. All right, now I just want to throw in some brief history. Isaac Newton and Leibniz are credited with co-discovering or inventing calculus, kind of in the late 1600s and early 1700s there. Brooke Taylor and Colin Maclaurin were English and Scottish mathematicians that are kind of recognized for applying their work of Newton and Leibniz in developing here what are named in their honor, Taylor and Maclaurin series. All right, the main advantage of this way to calculate a power series representation, we don't have to manipulate our function into the form 1 over 1 minus x. We can directly calculate the values for the nth coefficients by calculating an nth derivative, evaluating it at a or 0 in the case of a Maclaurin series, and then dividing by a matching n factorial. All right, now we're going to take a look at some standard examples in the remainder of this first part of this lecture. And probably the first example that every student in Calculus 2, when they get to Taylor-Maclaurin series sees, is probably a Maclaurin series for e to the x. Now, why is that? Why is e to the x a nice function to find a Maclaurin series for? Well, it may not have sunk in yet, but the main result of Taylor and Maclaurin series is we calculate the nth coefficients by calculating nth derivatives. What's nice about e to the x? Its first derivative, and for that matter, any order derivative is just e to the x. So it doesn't matter how many times you differentiate e to the x, the nth derivative is just e to the x. So we have the first part, a very simple formula for the nth derivative. For a Maclaurin series, we're going to evaluate that at the center point, 0. So we take our formula for the nth derivative, the nth derivative of x here is e to the x. We evaluate that at x equals 0. So we get e to the 0, which is 1. But this by itself is not the value of our nth coefficient c sub n. Recall, we need to divide the nth derivative by a matching factorial. So what we get, a very simple formula for c sub n, the nth derivative at 0, which is 1, but now it's divided by n factorial. And we basically have answered the question. We have a very simple formula for c sub n. This doesn't always happen. This is, again, a simple example. But we have a nice pattern here for c sub n, which holds for all values of n. And we get the Maclaurin series here, 1 over n factorial times x to the n. And notice for power series, we've been starting them with index value 0. And if we write out terms, we're calling 0 factorial equals 1. We get this power series representation, this Maclaurin series, for e to the x. Now, one question that we addressed for power series representations is for what values of x do they converge? And we actually did this example. I didn't tell you at the time what it was, but think back to when we covered in our lecture on power series, example 1, part C, we found by applying the ratio test that this power series has an interval of convergence -infinity to infinity. In other words, this power series converges for all values of x. All right, let's take a look at a second example, probably the next simplest example, a function that has some nice patterns to its derivatives, is sine of x. Now this one you want to make maybe make an attempt at, give yourself just a few minutes, but this is again gets to be fairly complicated, trying to extrapolate and generalize patterns. But give yourself a few minutes and we'll check in and go through it at that point. All right, welcome back. Before we start the calculus part, let's just do a brief review here from I guess pre-calc trig. Since we're asked to find a Maclaurin series, we're going to be evaluating the function and its derivatives at 0. Recall for a Maclaurin series, the center point is always 0. Now, if our function is sine of x, repeatedly differentiate that and you'll get sine or cosine of x with some extra factors of a negative appearing. So we're going to need the values for sine and cosine of 0. Recall a basic unit circle. We're going to think of x as being the angle in radians. So we have there in red the angle 0 radians, which corresponds to the point on the unit circle 1, 0. And recalling from the last time you covered this, maybe back to pre-calc, cosine values come from the x-coordinate, sine values come from the y-coordinate. So we have cosine of 0 as 1, sine of 0 equals 0. And again, we're working in radians. All right, at this point, the calculus shouldn't be so bad. Calculating successive derivatives, let's start with our function as sine of x and calculate a few derivatives. It's a little tricky, just keeping track of all the negatives that pop up. The first derivative is cosine of x. Recall the derivative of cosine is negative sine of x. And if you differentiate that negative sine of x, you'll get negative cosine of x. Now, notice what happens if you differentiate the third derivative. The derivative of negative cosine of x just comes back to sine of x, which is our original or starting function. If you were to again calculate successive derivatives, notice the fifth, sixth, and seventh order derivatives are the same as what's over on the left there. We get this pattern of every 4 terms, starting with sine, cosine, negative sine, and then negative cosine. So here you can see the terms cycle back, not every function and its derivative, like with e to the x, but every 4 terms and derivatives. All right, now for a Maclaurin series, we would evaluate these derivatives at 0. So let's go ahead and plug in x equals 0. From above, any function value with sine of x in it, sine of 0 is 0, and any function with a cosine of x in it is going to evaluate to either positive or negative 1. Now, we can kind of see maybe a pattern here. Notice any even ordered derivative term is 0. And that's because any even ordered term contains sine in it, or sine of x. All the non-zero terms come from those containing a cosine, and notice all the cosine terms are in the odd ordered derivatives. All right, so if we were to kind of, again, maybe hypothesize a formula seeing the pattern of these function values here, what we get is the value for an nth derivative, at least where the order is even. Notice the second derivative, the fourth derivative, the sixth derivative, those are all even ordered derivatives. Those are equal to 0. It is all the odd ordered derivatives, for instance, f prime, f triple prime, I don't want to say f quintuple prime, but the 5th order derivative and then the 7th order derivative, those are all then positive or negative 1. So if the order is even, and recall an even number is of the form 2 times an integer, an odd number is of the form 2 times an integer plus 1. After every even number is an odd number, that's the plus 1. We get this nice pattern. And if we go a little bit further, we can say f to the 2k order evaluated at 0 is 0, and the nth derivative where the order is 2k plus 1 evaluated at 0 would be negative 1 to the k. And notice those kind of statements there match the patterns of those values. So again, a little more work than e to the x. Basically, half the function values are 0. Those are all the even ordered derivatives. And all the odd ordered derivatives are non-zero, positive or negative 1. Now, if we plug these into the Maclaurin series representation for the function, we have our index n being summed over all integers going from 0 up to infinity. From what we see with our pattern for function values, let's split the index n into the terms that have n equal an even value, and then values for n that are odd. All right, if we sum over those two parts, we have the summation dealing with all the even index terms. That's where the n value equals 2k. We also have the part where the index n is then an odd value. That's where n equals 2k plus 1. And notice we plugged that in there, replaced n with either 2k or n with 2k plus 1 into the general expression, which was in terms of n. All right, if we use what we found right above, any even ordered derivative is going to be 0. So all of the terms in the even value of n and summation, those are all going to evaluate to 0. The only thing that is left is the odd index terms, and that's where the derivative, where the order is 2k plus 1, an odd order, that's going to be of the form -1 to the kth power, or k power. All right, at this point, we basically have our Maclaurin series. We're just going to re-express it on the next page. All the even index terms evaluate to 0, and it's only here the odd terms that survived, that had non-zero coefficients. All right, since we usually have used an index for our power series as n, let's change all the k's from the previous part, where we had 2k plus 1 appearing in a few spots. Let's just go ahead and replace that with n. The index doesn't matter, just like a variable doesn't matter. So let's switch all the k's back to our standard index n, and we have the Maclaurin series for sine of x. The nth coefficient here, provided we're looking at the odd terms, have the form -1 to the nth power, since there were some alternating signs. And then instead of having just n factorial, we have in these terms that survive, or the ones that are non-zero, a factorial, but now not for n factorial, but 2n plus 1. And the 2n plus 1, that came from the odd index terms, 2k plus 1 from before. And notice what we have? Not any power of x, but a power of x that is odd. We have in our summation x to the 2n plus 1. So we get this kind of nice looking Maclaurin series or power series representation. It only contains, for sine of x, the odd indexed terms, or odd powers of x. This one, if you apply the ratio test, you'll find its interval of convergence is also -∞ to infinity. So in other words, this power series converges for all values of x. All right, now we went through this example kind of in detail for the function sine of x. What you might want to try is repeating this, but instead for the function sine of x, the function cosine of x. It's really not any harder. It's pretty similar, just some things are kind of shifted a little bit. And if you were to go through this, it's a very similar argument and set of calculations to what we just looked at. You can find this Maclaurin series for cosine of x. Now, what we're left with is only the even indexed terms for cosine. And recall, an even number was of the form 2 times an integer. So this is the Maclaurin series for cosine of x. It also has an interval of convergence from -∞ to infinity, which you get by applying the ratio test. Now, these that we went through, the Maclaurin series for e to the x, sine of x, and cosine of x, are kind of extremely important for some applications in, I'll say, kind of some mid to high level physics and engineering courses that you might be taking. Before we end this part of the lecture, let's just take a look at kind of an interesting fact. Recall that sine of x was an odd function. And what we mean by odd is a particular type of symmetry. There's this algebraic property for an odd function. Plug -x into the function. You have a negative factor out front. So sine of -x equals negative sine of x. The graphical version for this statement about a function being odd is the graph has symmetry through the origin, a simultaneous reflection over the y and x-axis. So a twofold symmetry. All right, cosine is an even function. There's this algebraic property when you plug in a negative, you just get the same thing as plugging in the positive. So cosine of -x equals just cosine of x. The graphical version is an even function. Its graph is symmetric over the y-axis, a one-fold symmetry. Now, what's relevant about sine and cosine being odd and even functions, respectively? Well, take a look at the Maclaurin series. Sine of x, which is an odd function, its Maclaurin series only contains odd powers. Cosine, which is an even function, its Maclaurin series only contains even powers. And that's an interesting result. What we'll be looking at in part 2 are some of the more detailed ideas of issues regarding convergence to Taylor and Maclaurin series, and then an application.